Here's another spiral, the aloe vera plant. You ladies are quite familiar with this. Aloe vera is widely used in cosmetics. The sunflower, another spiral. That spiral allows for the greatest number of seeds to be packed in that area. And then we come to this little creature, Nantillus pompilius. And there's an eye for the little creature. This creature is a sea creature off the coasts of Vietnam, Cambodia, and into the ocean in that area. That's his shell, his home. Actually, it's his homes. And that's what it looks like if you cut the shell in half. There's something very appealing to that. I think it's quite beautiful how its symmetry shows. When the little fellow is born, let's call him Charlie. Charlie occupies a volume of 1. Doesn't matter what the units are. And then he starts growing and he says, it's getting tight in here. I'm going to make another home. He makes another one. Oh, that didn't turn out so well. I'm just as crowded in there as I was before. What's 1 plus 1? 2. He makes one twice as big. He grows. What's 2 plus 1? He makes another one. What's 3 plus 2? Okay, you got the picture? He keeps growing according to that pattern. The chamber volume is equal to this number. This is a number by a mathematician who lived about 900 years ago in Italy. And there's another number you know very well called pi. The ratio of the diameter to the circumference. It's called an irrational number in mathematics. Irrational because it never ends. It goes on and on and on. Let me introduce you to a new rational number. It's called the divine proportion, the golden ratio. If you divide 21 by 13, you get 1.615. 34 by 21, 1.619. So you see where this is going? Doris said I had to have some mathematics in here. And here it is. With a little geometry and algebra, you can derive this formula for phi. Take the square root of 5, add 1, divide by 2, and you get this big, endless number. The Parthenon in Athens, for example, has a ratio of 1.6 for the height of the building to its width. Here's another number. You start with this trunk with 1, add a branch 2, more branches 3, 5, 8, 13. Same type of progression. This sort of thing is all over in nature. Now if you look at this, look at the spiral. Like that. Now look at this famous painting. If you impose that spiral on it, look how it fits. I wonder if the artist knew about this mathematical relationship. Okay, now let's compare the humongous with the itsy bitsy. Here we have a Great Dane, probably around 160 pounds, with his close buddy, the Chihuahua, well, maybe 3-4 pounds. There's more to this picture than meets the eye. The Great Dane is blind, and the little Chihuahua is literally his seeing eye dog. Now, everybody knows about a glass of water, right? How many molecules are in there? I'm not going to wait for you to answer. There are that many. Lots and lots of molecules. Remember the number of stars in the observable universe? There are 8 times more molecules in that glass than there are stars in the universe. Molecules are small. The humongous and the itsy bitsy. Okay, back to the Milky Way. Now the distances are in miles. Here's a molecule of water. It's 0.27 nanometers across, which means nothing to any of you. But the average hair, human hair, is 50,000 nanometers in diameter. 50,000. the molecule of water is 1/4 of a nanometer. So that puts it in perspective. It's tiny. Water again, and this is its closest molecular cousin. They're first cousins. Water boils, as everybody knows, 212 degrees Fahrenheit. Any guesses to the boiling point of hydrogen sulfide? I don't think I'm going to hear anything. Minus 76 degrees Fahrenheit. Now, you've all encountered hydrogen sulfide. Ever smell a rotten egg? Hydrogen sulfide. Now, why do these two very similar molecular compounds have such a wide variation in boiling point, you ask? Let me explain. Up there you see 4 molecules of water. Oxygen is the red one, and hydrogen is often the little white circles. And the hydrogen, here's the scientific explanation. Are you ready for this? The hydrogen says to the oxygen, "Hey, Oxy, you've got a lot of electrons and I don't. Can I snuggle up to you?" And the oxygen says, "Sure, Heidi, come on, snuggle up." Now, water compresses itself, it packs in together. In order to break those bonds, it takes a lot of energy, hence the high boiling point. And those bonds are called hydrogen bonds, and they play a critical role in DNA. We'll get there. Now, just a couple definitions. First of all, DNA stands for deoxyribonucleic acid, but that's such a mouthful to say, everybody says DNA. Now I'm going to talk about genes. Not that kind. The GENE type. This is a particular piece of DNA that tells a cell how to function. It tells a brain cell to fire a synapse, for example. It tells a kidney to make some urine. The DNA is the plan. The genome is the entire content of genetic material in an organism. There's a human genome, for example. And I'll talk a little bit more about that in a minute. The human genome contains about 100,000 genes. And the function of these, about 6,000 of them, have been sorted out and identified. So that leaves another 94,000 to work on to figure out what they do. So there's enough research here to keep a bunch of scientists busy a very long time. Now DNA, finally, here we go. It was first discovered in 1869. That's 150 some years ago. It is the molecular blueprint of who we are. My DNA says my eyes are blue, your eyes are brown. It says you men are handsome, you ladies are beautiful. Did I say my eyes are blue? It's the blueprint. It's present in every one of our cells. We have billions of cells, but there's a DNA in there. It also regulates the creation of proteins that are essential for cells to perform their functions. So it's the blueprint of who we are, and it is also the blueprint for producing these proteins that make cells work. DNA self-replicates. Every time a new cell is created, the DNA is transferred to it. You, Lord, make all the delicate inner parts of my body and knit me together in my mother's womb. From, again, Psalms. Now, the psalmist didn't know about all this, but he had the overall picture right down to the T. Now, DNA is an enigma. It's a very complex substance, but it's composed of only 6 components. Just 6. It's a fragile substance that can be readily damaged, but it's stable for thousands of years. It's capable of holding vast amounts of information in an extremely small space. And I'll go over all of these points in a bit. It's a natural medium for information storage, and you'll see more about that in a minute. It can repair itself. It can heal mutations. Mutations are caused by ionizing radiation, which is all around us all the time. Also during cell division, mistakes are made to create a mutant, and things like mutagenic chemicals, which we all are exposed to, also cause these problems. Now I want to talk about an editing tool, a DNA editing tool called CRISPR-Cas9. Never mind what it stands for. But this is a way to alter DNA. It's been used successfully to treat sickle cell anemia. Sickle cell anemia occurs in about 1 in 365 black people. It's a real debilitating disease, and it's very difficult to treat. It's been used successfully to treat Leber congenital amaurosis, which is blindness in children. Children with this genetic condition are born with weak eyesight, but they very quickly, in a matter of a few years, go completely blind. This technology certainly has the potential for both good and evil. There are some real serious ethical issues that have to be dealt with in this. Two ladies, Jennifer Doudna and Manuel Carpentier, won the Nobel Prize in Chemistry 2 years ago. Yeah, that's right. For developing this technology. And here they are in the Nobel Prize auditorium. Usually what you see are old bald men and some with beards who are getting the Nobel Prize. But these two ladies were the first time the Nobel Prize was awarded to two women. Carpentier is the director of a Max Planck Institute in Berlin, and Doudna is a professor of chemistry at the University of California in Berkeley. Now, DNA provides the code for a cell's activities. RNA, ribonucleic acid, converts that code into proteins that carry out cellular functions. Now, don't get excited about this. All this is, there are 7 different approaches for looking at how to develop drugs. And what caught my eye was right at the bottom, there's a thing mentioning patient customization. The idea here is to use this technology, the CRISPR-Cas9, to alter a DNA that can then serve as a drug for treating conditions. Not only genetic diseases, but heart diseases, cancer, and so on and so forth. And the goal with this development is to be able to create a class of drugs which then can be used to treat a disease by examining the patient's DNA profile. So you associate the DNA profile of certain cells with the drug, and you pick the drug then which is most effective. There's also a hope that eventually you will be able to look at a certain DNA pattern in a patient with a disease and then quickly manufacture the most efficacious drug specifically for that patient. I mean, it sounds impossible, but it may well come to that. This is hot off the press, so to speak. I just saw this example in a journal 2 or 3 days ago. Now, identical twins. Are they identical? Well, not exactly. The answer is no, they're not identical at all. They may look alike, but no, they don't even have identical fingerprints. They are identical for a very brief period of time when the egg in the mother's womb divides to form the two twins. At that point, their DNA is identical. But then we have ionizing radiation and all the rest of it, and the DNA does change. Now, all humankind shares 99.9% of DNA. We are all much more alike than we are different. That means there's only one part in 1,000 that uniquely defines us. Now, let me go on here. There's a song, a children's song called "You're Something Special." This was sung by the Gaither group some years ago. God gave you a body and a bright, healthy mind. He had a special purpose that he wanted you to find. So he made you something special. You're only one of your kind. Each one of us is unique. And Anna's sitting there saying, "Oh, that's good. There's only one of him around." With only one part in a thousand different, this makes Pastor Daniel and I almost identical twins. I mean, except we had different parents. But truly, we are all very much alike. Now, where do you find DNA? Obviously, in humans, cats, dogs, and salamanders, sunflowers, corn, mushrooms, and strawberries, bacteria and viruses. Well, but viruses are not considered living organisms. They are, in essence, complex molecules. Unless a virus finds a host, it cannot multiply and divide. So by itself, there's no way it's going to live. It eventually just sort of disintegrates. DNA has also been found in bones, human bones that were 400,000 years old. Now, when you bury something, that is not an ideal storage place. Things deteriorate. But this shows you the stability of DNA. That DNA can be analyzed like any other DNA. So it's remarkably stable. All living things have DNA. All. There's no exceptions. Now, is there anything in common between a human and a banana? This will be surprising. I'm going to show you the percent of DNA that's shared between humans and other organisms. First, look at the banana. 40%. Now, before you get upset, let me explain a couple things. This shared DNA means a commonality of DNA segments, not the whole genes, segments. And various studies use different segment sizes to calculate these numbers. And then much of DNA in any organism is silent. It's just there as part of the structure. It doesn't take any part in any of the coding. So the numbers depend upon how you estimate the overlap. For example, the chimpanzee, we share 98.7% of our DNA. Well, that's not surprising. Both have 2 eyes, 2 ears, a brain, usually have a brain, 1 heart, 2 lungs, 2 kidneys, 1 liver, 2 arms, 2 legs, 10 fingers, and so on. The pig, 98%. Some of our Jewish friends might get a little upset over this, but I'm afraid that's what it is. Pig skin, for example, is used in testing of cosmetics because it's so much like the human skin. And then we have cat, mouse, dogs, so on, all sharing a certain amount of DNA. Yeah, the slug, we got the slug. So the next time you call somebody a dirty rat, just remember 69% of the DNA is in common. Now, the analysis of DNA enables a number of things. The identification of human remains, paternity identification, forensic identification of criminals, exoneration of wrongly convicted, diagnosis of hereditary diseases, leads for drug development, which I already mentioned, detection of infectious pathogens, and ancestry tracking, which has become very popular. Now, as of 2021, there were almost 1 billion people who had purchased ancestry tracking kits. How many here have had their ancestry tracked? A good number. Here are 10 companies that offer test kits. These are the most popular ones. I really have not looked into this in any detail. The prices range from $70 to $400. However, 20 years ago, 25 years ago, to do an analysis like this cost thousands of dollars. Now it's really very inexpensive. Now, what does DNA look like? There you go. It's that white slimy stuff in the spoon. That's the DNA from strawberries. If you Google strawberries and DNA on the web, you'll find all kinds of recipes for doing this. It's called kitchen chemistry. Now, DNA consists of 6 simple molecules. I'm going to show them to you. Phosphoric acid. which you get out of rocks. I'm giving you the price of each of these because you can buy them from chemical supply houses. Deoxyribose, which is a very simple sugar. It is much more simple of a sugar than sucrose, which we put in coffee, tea, cookies, and so forth. And these four things, adenine, guanine, cytosine, and thymine, usually they're just called AGCT for simplification. Adenine and guanine, the two on the left, are quite similar. There's a 6-membered ring and a 5-membered ring attached to it. Cytosine and thymine just have a single 6-membered ring. Now, these compounds could be synthesized by an undergraduate. Well, not an undergraduate majoring in history, perhaps, but one that's majoring in chemistry. By the time they're a junior or senior, they could make these in the lab. They're indeed simple. Deoxyribose is more complicated for reasons I won't go into. A single human strand of DNA is about 2 inches long if you stretch it out. But remember, it's in a tiny cell, so it's packed together in there. But it's a big molecule. Now, how do these 6 simple molecules fit together? A little background. How many of you have seen a ring around the moon? Yeah? Yeah. It's more common farther north than here. But it occurs, actually there are several rings around the moon. And that's caused by the diffraction of moonlight that hits ice crystals up in the atmosphere. If you shine a beam of X-rays into a crystalline DNA, the X-rays are scattered to a pattern. And if you put a piece of film in back of it, you capture a picture. And this is what that picture looks like. Historically, this is a very famous photograph. It was created by a young woman named Rosalind Franklin, who you've probably never heard of, and was published in a journal called Acta Crystallographica in 1953. Now you see that little circle? My pointer isn't going to work. Little circle in the center. That's a highly sophisticated scientific piece of equipment called a paperclip. The DNA is wrapped around the paperclip. Here's Rosalind Franklin on the cover of Time magazine in 1953, holding up that picture. She was had a PhD in physical chemistry from Cambridge. She passed away in 1958 at the age of 38 of ovarian cancer. She worked with X-rays for years, and at that time, not as much was known about the danger of X-rays as there is today. In fact, in the 1950s, you could go into a shoe store and stick your feet into a little machine that took a picture of your shoes and your feet, and you could see your bones. It's a fluoroscope. Every kid that ever walked by a shoe store went in there to look at his bones. Well, fortunately, that came to a stop because this is dangerous stuff. Here are 2 gentlemen, James Watson and Francis Crick, explaining what DNA looks like. That's not very helpful. And here's James saying, hey, it's a spiral. In 1962, these 2 gentlemen and Maurice Wilkins received the Nobel Prize in Physiology and Medicine for explaining what DNA looks like. In other words, its structure. Now, remember this? The hydrogen bonding. Adenine bonds with thymine, and guanine binds with cytosine. And the bonding is through hydrogen bonding. Hydrogen also bonds with nitrogen for the same reason it bonds with oxygen. And these bonds are really, they're low energy bonds, but you have so many of them, they're really tight. Adenine does not bond with cytosine, and guanine does not bond with thymine, okay? So we just have A, T, and G, C bonding. This is critically important and interesting. AT bonding can represent a 1, and GC bonding can represent a 0. Does this sound familiar to anybody? binary number system. Your cell phone uses binaries, computers. If you bought any appliance in the last 10 years, your washing machine uses it, everything uses binary numbers. More on that in a bit. If you take a piece of DNA from a chromosome, uncoil it and lay it flat, you will see ACGT on one side and the other side ACGT. You see AT bondings and CG bondings, but not AC and GT. This is a pretty good representation of DNA. It's a right-handed double helix that is spinning around this way. And the blue coils, the strips, are the sugar phosphate backbone. And those two coils are held together by the hydrogen bonding of AT and CG. Very elegant. And those are called base pairs. This is another famous photograph. This was published in Nano Letters in 2012. That dark you see in the middle is the bonding between those two spirals. Now, this is done with an electron microscope. In an ordinary microscope, you use visible light. That's much too long wavelength to see molecules. So this is a stream of electrons that are used to make the image. Now, just as a reminder, the genome is genetic material, the whole genetic material of an organism. And I want to talk now about the Human Genome Project. It ran for 13 years, from 1990 to 2003, and then it was declared a success. I'll show you what the objectives are of this. This is at a cost of $3 billion, which was paid for by our tax money. It's the world's largest collaborative biological project. And here are the institutions that have been involved with it. There are 20 of them, most in the United States, but some in Europe and some in Asia and Japan. And when it was completed, they had a good chunk of all these base pairs analyzed. But it wasn't until December of last year that it was finished. So it took from 1990 until 2022 to do the full analysis of the human genome. It's a remarkable accomplishment. Now, the objectives of this project were to identify all 20 to 25,000 genes in the human DNA. The exact number wasn't known when it started. Probably still a number that have been quite identified. And it was also to determine the sequences, the pairings of about 3 billion base pairs in the human genome. And as I said, that was completed in December of last year. One other goal that was to improve tools for DNA analysis, which it certainly did. So now the cost of a DNA analysis is $100 or so. In 1990, it was many thousands of dollars. Now, what are the benefits? Well, certainly improvements in medical diagnoses. Leads to gene therapies to treat diseases, which I've already talked about. Improvements in agriculture and livestock breeding. Now, I realize that GMO is a controversial issue. Many people do not want to eat foods that have been genetically modified. But let me give you an example. Corn stems from a type of a grass, which had one area in it, maybe half an inch or a quarter of an inch long, which eventually became the cob. But that was the tastiest part of the grass. So farmers would then use the seeds from the plants that had the biggest cob in it. And over hundreds of years, that cob grew and grew until it became about this long. And on that cob are kernels of corn. In the 1950s, it was learned that you didn't have to just pick out the best seeds. You could physically alter the DNA in the corn and improve it. And this is now known as genetically modified material. When I was a boy in Iowa, I lived on a farm, a good crop of corn was 100 bushels an acre. Today it's 200 bushels an acre. The same improvements were done with rice, which is a major grain for much of the world. Had not this progress occurred, our price of food would be much, much higher today, and there'd be many thousands of people who would starve. So yes, there is some risk, but as far as I know, no problem has been caused yet by a GMO modified substance. We'll see how it all pans out. Of course, this also leads to a greater understanding of human and animal plant biology. Now, has any digital data been stored in synthetic DNA? I'm talking synthetic DNA, nothing from a mouse or a cat, but this is DNA that you make in a laboratory. Well, the first moving picture, the galloping mare, has been stored in DNA. A $50 Amazon gift card. Good luck in reclaiming that one. Tolstoy's War and Peace. A bilingual version of the Bible. All of Wikipedia in English. And a lot more. A lot more. So how much digital stuff can be stored in synthetic DNA? About 200,000 terabytes in a gram. Now, a gram is 1/28 of an ounce. 200,000 terabytes is a little hard to wrap your head around. But let me put it this way. Almost 5 billion copies of the King James Version of the Bible can be stored in 1 gram. That's a lot of stuff. So what is being stored is at a molecular level. The current technology, the disk drive, for example, will last 5 to 8 years. Solid state storage lasts about 10, 12 years. There are methods to store it on optical disks that maybe will last 100 years. But stuff stored in DNA will last thousands of years, if not millions. Now, there are some challenges in DNA storage. It's very expensive and slow to encode and decode. But let me remind you a little history here. That thing they're loading on the airplane is a disk drive. It's manufactured by IBM. This is in 1956. It had a capacity of 5 megabytes. If you take 2 pictures with your cell phone, that'll take up 5 megabytes. You couldn't buy it. You had to rent it at almost $32,000 a month. They didn't sell a huge number of them, but that was the state of technology of disk storage, of information storage in 1956. Today you can buy a thumb drive for $14 that holds 25,000 times more storage. Now the question is, will DNA follow a similar path? Companies like Microsoft and Google and IBM and Amazon are spending millions of dollars in research on this because this holds a great deal of promise. If you go out to Ashburn along the W&O trail, you'll see all these big server farms, one huge building after another. Each of those big buildings holds 40 to 60,000 computers. If you can pack all of that into a suitcase, imagine the money you would save. And God said, I have placed my rainbow in the clouds. It is a sign of my covenant with you and with all the earth. We've all seen rainbows. In 1905, this young man published a paper in a German science journal, a physics journal called Annandale der Physik. And the title of the paper was about a heuristic point of view concerning the production and transformation of light. That doesn't tell you a thing, does it? Well, one of the things he wrote was light consists of particles, which he called quanta, with energy proportional to their frequency. There's the higher the frequency, the higher the energy. Higher frequency things like X-ray have lots of energy. Visible light has lower frequency, lower energy. And he also wrote, these light particles have mass. These little particles of light weigh something. How weird is that? Anybody know who this guy is? Yeah. Yep. Here's the man. In 1905, he wrote 4 papers which changed the world. And this was the beginning, along with Max Planck, of quantum chemistry, quantum physics, quantum mechanics. It's all the same stuff. And I'm not going to go into this equation. It's highly nuanced. It's a very simple equation equating energy and mass, but there's a lot to it. You never know what beauty holds until you see it in little things. This is a poem from Destiny Hendrick. So the next time you think you know all the world has to offer, look for the beauty in little things. Imagine developing a plan written in 6 simple molecules that defines all living things. I mean to tell you, that's pretty fantastic. So the realm of the very small does indeed declare the glory of God. So many thanks. We've finished a bit early. Appreciate it.
Thank you so much, Professor. As you can see, there's a lot for us to wrap our minds around, but he's giving us some basic tools that we can kind of think and maybe use and apply in our own kind of little way, thinking about the science of DNA. This is really fascinating stuff. I think we probably should kind of do it again another time to break it even down more for some of us to kind of think about it. But let's just put our hands together again and express our thanks.
Thank you very much.
Thank you. As I shared with you, we're so lucky that we kind of were able to pull this off, and look at all of you here, kind of our first combined Sunday after, let's say, the pandemic, and this is really good. So we'll do it again another time. And we want you to suddenly come and participate in this. And I'm going to talk to Lorrin again, and maybe we'll have another session of this, kind of to even break it down more for us, to think about. But he made a point. We have about maybe 8 minutes, so we can open it up for comments and questions. But there's something that I'm taking from here. He and I are cousins, or brothers, So. I'm black, but we're all the same. Now, that's really fascinating, and so I think this is something that we can take, So God made us. And I think in the book of Acts, chapter 17, Paul talks when he goes to the Areopagus, Mars Hill, and talking about all the things he sees, God made us from just one family, from our ancestors, and we are all kind of branched into different areas, and our skin, things change, but we are basically the same people. And that's really fascinating. That talks about the God that we serve. So let me open it up for any question, comment at this point, and then we go from there. Yes, there's some mics on your... Yes, thank you.
Well, I'll just make a comment. My son in 2015 had a gene therapy operation to helpfully help Parkinson's disease. It was a 12-hour, $6 million operation that wasn't as successful as hoped, but anyhow, they've been working on this for a while now, but it does show real promise in medicine.
No questions, comments? Is that it? Okay. Yeah. Yeah.
You knew I had one. I warned you. Now, what does DNA look like? Is it a plasma? Is it liquid? How would you store stuff in it?
Well, what it looks like, you saw the picture with the strawberry DNA, that's what it looks like. When you extract it from any organism, including us, it comes out like a thick, gooey material. Now, you can crystallize it. Crystallizing things like DNA and peptides and proteins is difficult. I can remember when I was working on some peptide synthesis, I had in a flask some peptides in a solution. I was trying to crystallize it. I had it in the refrigerator. It didn't crystallize until 3 months later. I mean, it's a real pain in the neck. But you can crystallize DNA. And then it becomes a sort of a solid. It looks like a plastic at that point. Not transparent, but kind of a plasticky like material. Yeah.
You lost me at, I don't know if you can even explain it to me quickly. Artificial DNA. So, what do you mean? How do they do that? I mean, it's God-made, artificial DNA.
Okay. The DNA that's in us and all other organisms is manufactured within us by a series of reactions in the body. If you go to a chemical supply house and you buy those 6 chemicals in bottles, you then go into the lab and there are procedures how you can put it all together to make DNA. It's not horribly complex, but it's not for an undergraduate either. So you can actually, with those 6 materials, you can synthesize synthetic DNA. It looks X-ray crystallography. It's a double helix. There is this bonding, as I described before, but it has no biological information in it. Does that help? Yes. Okay.
Sir, your presentation was fabulous, especially to a layperson. One of the questions I have, though, is on the genetically modified organisms. Politically, I understand from an intellectual property side, that's where most of the debate really is. Countries being very reticent to accept something trademarked in Germany versus the United States.
Yeah.
However, from a dietary perspective, would you not agree that there have, over the last 3-4 decades, especially in the advent of processed types foods, there's been some change in the way that the bodies are reacting to nutrients? Just curious, because I know that's a whole discussion by itself, but you had stated, I think from a scientific perspective, that GMOs don't necessarily, I mean, it's very complex itself, but GMOs in general, to your, just trying to confirm, you don't see any implications whatsoever from a genetic standpoint of it impacting, say, populations?
Yeah, okay. Fair enough. Yes?
Lauren, what's your take? I know it's controversial, but you cannot change your DNA. With what's going on in the world today, especially with young kids wanting to change their sex, is that wrong as Christians? Is that wrong for us to say that is wrong? Or do we just keep our mouth shut?
I'm not.
Good luck.
I'm not going there. I'm talking chemistry. You're going to have to ask somebody else that question. I'm dodging it.
Let me, before Daniel,
Yes.
that's okay. I just go one quick comment. So months ago, and I can't remember when, I made a passing comment in the service about how some of our early modern scientists, when they were discovering and coming up with innovations in mathematics and in physics and so forth, that almost all of them took themselves to be, as they learned more and more about how our world works and how creation works, they took themselves to be learning more and more about the mind of God. And I think that's terribly important for us as Christians to keep in mind. You know, science is a method of us discovering truths that are deeply embedded in what God has done. And so the kind of skepticism that you sometimes hear on, you know, television or radio hosts and so forth, just railing against science and scientists, I would ask you to slow down with that a minute and appreciate that science seeks to understand how the world works. It's theology and philosophy that tells you why. But science is meant to tell us how things work. And they've done it brilliantly now for 300 years, and it's been largely to our advantage. And so I'm deeply, deeply appreciative of Lauren's presentation and this congregation's willingness to hear these insights that are directly related to what God is up to. That's it.
Thank you. Thank you. Do we have any? Our time is up, and as I said, this is just the beginning of great things, to come. So I think just tagging on to what Jeff said, God is the greatest scientist, and so I think what we've learned, right. I think that confirmed. Now, before we go, I have a little presentation, and I'm going to call on our own Greg Porter. Please, Greg, just come up here. Just give us a little kind of explanation, and then we'll make that presentation. I want everyone to watch. This is really fascinating, interesting.
First off, there's probably a pretty good chance that Jane and I are the only corn farmers in here. And we are grateful for the fact that we are looking for a yield of maybe 160 bushels an acre. When I was a kid, 60 was a good yield in Shenandoah County. Now, some of you will go shopping for certain things that you like, and others, like the Garsons, will make a pilgrimage. Would you come up here, please? We have a little token of our affection for you.
Oh, thank you very much.
Not the bag. I get to keep the bag.
Oh,
It's what's in the bag.
I see. I thought I was getting a bag.
Route 11 Potato Chips of Mount Jackson, Virginia, has a factory about 6 miles south of our home.
There you go.
And the Garsons will make their pilgrimage several times a year to get their potato chips from the Route 11. They really are good potato chips. And thank you for your faithful participation in our class and our church. And, if you'd been one of my professors, maybe I would have continued with my ag degree instead of switching to history. It was organic chemistry that did it.
Thank you.
Thank you all. Let me just conclude our time with prayer, and then we will break out for more fellowship out there. Gracious Lord, we thank you for the science of DNA and for all that it demonstrates to us, pointing to the ultimate brain, master architect behind all the things that we see around us, God himself, the greatest scientist ever. And so, Lord, may we go forth from here confident in the knowledge that you are our God. You made us and you redeemed us. And ultimately one day, we're going to meet you face to face, and we will understand all the mysteries that we are just trying to take a peek at, just to gain some depth into who you are and the way you have put us together. Bless us now, and as we transition to our worship service, may we continue to delight in you and rejoice in who you are. For it is in your name and for your sake we pray. Amen. Thank you all. God bless.